Okay, so do you have any questions before we begin? Okay. Okay, so here's the question. Your friend is asking, we know that in inelastic collision, the energy is not conserved. But nevertheless, the velocity of the center of mass does not change. So where does the energy go? Anybody who wants to answer? Anybody who knows the answer? What happens to the lost energy? Dissipates, what does that mean? It is basically converted into internal energy. So for example, when two objects collide and stick together, two cars colliding and sticking together, if you ever, I hope you don't witness a collision from nearby, but if you ever happen to take part in a collision, after the collision, go and touch the part that has been deformed. You will see that it is warmer. Okay, so then the next question. We know that the change in the kinetic, we had said that the change in the kinetic energy of a system is equal to the work done on the system, the total work done on the system. This we also said. Well, we have an inelastic collision. There is no external force to do work. But so then the kinetic energy shouldn't change. But nevertheless, he says that the kinetic energy is changing, right? Any comments on this one? So his first question was, in an inelastic collision, we said that energy is not conserved. So there shouldn't be any, there is an energy change. So what happens to the energy? Some of your friends said that, okay, that energy is converted into internal energy. Well, part of this internal energy is what we call heat. So the system will be heated up if there is this inelastic collision. Then the next question, he says that, okay, the kinetic energy, the change in the kinetic energy is equal to the work done, the total work done on the system. Well, there is no force, there is no external force acting on the system. So this tells me that the kinetic energy of the system should not change, but it does change. So how are these things consistent with each other?
Begin to accelerate, so kinetic energy, total kinetic energy does not change.
Okay.
Total kinetic energy of particles does not change.
So your answer is the total kinetic energy of all the individual particles do not change. So the total work done on the system is zero. So the change in the kinetic energy is zero. Although the apparent kinetic energy seems to change, some of it is converted into what we call the internal energy, which is nothing but the kinetic energy of the internal particles. Well, there's just one catch over there. This part of this internal energy is potential energy, not kinetic energy. What we call, for example, deformation energy. It is basically the potential energy stored in the deformation of the system. Now, the system will be deformed if the atoms, they change their shape, their relative separation will change. Well, we had already discussed that we can model the interaction of atoms in a solid as if they are connected by springs. So if their relative orientation change, part of the internal energy will be the potential energy, not only the kinetic energy. Any other comments on this topic? So let us look at this one. What is this kinetic energy of? Now here we wrote such an equation. We said that the change in the kinetic energy of the system is equal to the total work done on the system. But what is that kinetic energy? Well, forget about the potential energy. The potential energy is in this part, the work done. The change in the potential energy is nothing but the work done by the force creating the potential energy. Well, when we were discussing this equation, we were mainly dealing with point objects. We were dealing with point objects. We were defining their kinetic energy. So this equation made all the sense. Now we are discussing extended object or systems made up of many particles, not just one of them. But we had already seen that we can still treat our system as if it is a point, at least under certain circumstances, if we take that point to be the center of mass. So this equation is still valid for the motion of the center of mass. Now whether we have an elastic collision or an inelastic collision, the kinetic energy of the center of the velocity of the center of mass, and hence the kinetic energy corresponding to the motion of the center of mass, doesn't change. It is zero. And as you said, in a collision, whether it is elastic or inelastic, the kinetic energy corresponding to the corresponding to the motion of the center of mass is the same. This is zero. Well, as you said, there is no external force acting on my system. So the total external work done on my system is zero. So this equation is still valid as long as you interpret this change in the kinetic energy as the kinetic energy of the center of mass motion. Now the other part is we had also, if you remember, we had also derived that the kinetic energy of the whole system, or of this two-particle system, we wrote this as 1/2 the center of mass squared plus 1/2 m1 m2 over m1 plus m2 times the relative motion squared. We also wrote this one. This is basically if you just sum the kinetic energies of both of those parts. We had point mass 1, point mass 2. So if you just sum their kinetic energies, this is what you get. Now this part is mainly you can say that it's an internal energy of the whole system. If you look at the whole system is moving with this velocity. It has this kinetic energy. Plus there's an internal motion of the system, the motion of the parts making the system, they are also moving relative to each other. It is this part. And that is mainly what we call the internal energy of the system. So what happens in a collision, is mainly internal energy is converted to other forms of internal energy. Now things are getting complicated. One of the reasons is that up to now we were always talking about our system, the system. Now what is our system? Which system are we looking at as the system that we are studying? Now there are many ways of doing that. For two-particle system, you can say that I have two systems interacting with each other. Mass 1, mass 2, they collide. So this is a valid description. Or I can say that the whole thing is my system. This is another description of the system, of the process. So if you look at the whole thing as your system, in that case, this is the kinetic energy of your system. This is the internal energy of your system. And in a collision, it's just the internal energy that changes to some other form of internal energy. And this is still valid for your system. There are no external forces. And the kinetic energy of your system as a whole, the change in the kinetic energy of your system as a whole is still equal to the total work done on your system. Now there are all these different perspectives that you can approach a given problem, and all of them are true. So whichever one you want to choose, you can choose whichever one you want. If you are doing the proper thing, all of them should give you the same answer, and all of them will be correct. Well, the details can be quite complicated. Because, well, you see, in a collision, does anybody have a gum? For example, that will be an inelastic collision. If you just take a gum which is already chewed, hit it with this ball with the gum, the shape of the gum will change, right? The shape of the basketball will not change, but the shape of the gum will change. Now that change in the shape would mean there is a change in the internal energy. That is one change in the internal energy.
For example,
Heat is another form of change in the internal energy. Other questions? Other questions about rotations? Come on, about rotations you should be asking hundreds of questions now. It is probably one of the hardest topics that we have studied until now. It will get harder, and I don't think there are just more than a couple of people who are actually following. Yes?
when we are examining the kinetic energy of a rotating body, always use center of mass.
Okay, up to now, at least up to our last lecture, what we dealt was objects rotating around an axis that is fixed, that is not moving. So the kinetic energy of rotation of that object was equal to 1 over 2 I omega squared. This is the kinetic energy of rotation. It's not, the rotation axis is not necessarily the center of mass, but the important thing is that it should be fixed. In the last hour on Tuesday, we started studying systems that are moving also. There things started to get again a bit more complicated, because if your axis of rotation is fixed, well, there's no ambiguity in choosing that axis of rotation. But if it is not fixed, if you allow your axis of rotation to move, then you have all this freedom of choosing the axis of rotation. And if you remember, we said that, as an example, I had this wheel. Okay, if this is fixed, the wheel is rotating in the counterclockwise sense, then what's the direction of the angular velocity? Towards you. Okay, so it was clear. We had a fixed axis, everything is fine. But I can also have, we also said that this is the rotation axis. But the same system I can also describe as, okay, this is the rotation axis. But this time the rotation axis is also moving. These two descriptions are both valid descriptions. And in one case, if I want to calculate the kinetic energy of rotation, I should take the moment of inertia around this axis. If I want to calculate the kinetic energy of rotations from this perspective, I should take the moment of inertia around this axis. They will be different. The kinetic energy of what we call the kinetic energy of rotation in both cases will be different. They will look different. But of course, the total kinetic energy of the system should be the same in both cases, because the kinetic energy, whether it is of rotation or of translational motion, we just said that, okay, we just divide our system into point-like objects, calculate the kinetic energy of each one of them, and then sum them up. This way of describing this rotation and this way of describing the rotation, they should give me, well, this point has a given velocity, whether I use this description or this description. It doesn't change. Also, another point, I'm not changing my reference frame. I already choose one reference frame, I'm fixed there. Then I want to describe rotations. And we said that if we want to describe rotation, I have to specify the rotation axis, and then how much it rotates, what's the angular velocity, etc., relative to that axis. Now, this is what we are doing over here, is that we have this freedom of choice in our description, in our choice of the rotation axis. I can choose the rotation axis to be here, the rotation axis to be here. But whatever description I choose, the velocity of this point is fixed because I have already chosen one reference frame and I'm fixed there. The kinetic energy of this point, the kinetic energy of this point, they are fixed. They have to be the same. The kinetic energies. Nevertheless, what we actually are doing is, we will do today, we are splitting the total kinetic energy of an object. We will see that we can split the kinetic energy of an object into its kinetic energy of the center of mass plus the kinetic energy of the rotation around an axis passing through the center of mass. Now we can also split it through an axis that is not going through the center of mass, but then things will get more complicated. So we will most of the time avoid that choice. But even that choice would be valid. Yes, other questions? Yeah, I would rather review past subjects than continue without you following me. So if you have any questions, if there's anything that's not clear, anybody else? Yes.
What if the body is rigid, such as sun or stars? Can be some particles motion and erect center of motion and apply it for velocity?
Sure. I mean, when you don't have rigid body, talking about rotations is also kind of not so, it's a bit messy. You can still do that. Now, when you have non-rigid objects like this one, I mean, here we said that, okay, we have these two objects colliding, this one and this one, they are moving towards each other, colliding, and afterwards they will be moving in some different directions. You can just, this is a non-rigid body as a whole. Well, there are only very few particles in this body, but as a whole it's a non-rigid body because it's constantly changing its shape. You can just generalize this into many objects, many particles, many point particles, like, as you said, a gas or a star, I don't know, whatever you want. And you can still do this separation, the motion of the center of mass and the relative motion of each one of the particles relative to the center of mass. And this will be, well, for the rigid bodies, we can parameterize these simply in terms of a single parameter, what we call the angular velocity for rigid objects. For non-rigid objects like a gas cloud, etc., well, it will be very hard to reduce this into, to describe this, what is the kinetic, relative kinetic energy in terms of just a few parameters. But still you can do that. But just angular rotation would not be enough. You should specify other parameters. Now, in a rigid object, you see the angular velocity, if you just rotate this ball, let's say, let's rotate it. Now, there's an angular velocity of this ball. You can say, okay, you can then talk about the angular velocity of this point, of this point, of this point, and they will all be the same. If you choose a different rotation axis, still the angular velocity around that axis will still be the same for whichever axis you choose. You can even choose your axis of rotations to be somewhere outside. It doesn't even have to be in your body. But then the motion of the rotation axis will be really complicated.
Maybe after this lesson you can pass this rotation subject. But may I one favor from you? And just write the one example, and this example includes rotation, everything. And I want to understand what is the rotation, how can I apply the all learning things. And I don't want to forget the rotation side. Still, I'm confused and I cannot solve it well.
Okay, this one we will be solving it. We will be studying this motion. Would that be satisfactory for you? Or you have another example, a more complicated one?
This example is not for me.
You tell me the example.
Well, it is not a specific example. Just, after someone asks me, what is rotation? How can I solve this question? Someone will come and hear me and ask. But if I cannot solve this question, something is wrong. And then we will pass this. Already I studied, but nothing happened. And then just I want to see the last example. And would you like to solve?
I mean, which example? Well, this one is one example that we will solve if you don't like.
This explanation not enough for you because where's the math, where's the physical calculation?
We will do the calculation of this one, don't worry.
All right.
I mean, we had just began to do it in this example. We will continue with that. But you don't like it? Well, you see, there's also another point. You see, at least my way of looking at it, there is this physics, the science, and the engineering part. Now, the science part is basically related with fundamentals. What are the fundamental principles? The engineering part is filling in the details. Like, for example, we are ignoring friction. We are ignoring friction because it makes easier to calculate, to demonstrate some fundamental properties. Can we add friction? Well, it's just a force. We should add the force, and then the equations we get will be quite complicated. We can invent quite complicated motion, but nevertheless, the fundamental principles will be the same. There is no change in the fundamental principles. And those are the things that we would like to concentrate. Now, furthermore, in this year, one nice thing about your first year courses will be you will be covering almost everything you will be seeing in the next 3-4 years, almost everything. But in a basic level. In the future years, we will be studying the same problem with a more complicated mathematics, for example, in rotations. Now, we are dealing with very simple rotations. The axis is fixed. Now, we are allowing the axis to translate. We are allowing the motion of the axis, but nevertheless, the rotation axis, its orientation is still fixed. It's not because we cannot deal with rotations in which the rotation axis will be quite complicated, and the motion can be really complicated, but they will not be really teaching you more new principles. The fundamentals, even if in a much more complicated example, will be the same. And you will be dealing with such examples in your third year.
In this example, when the ball is rolling down at some point, why the direction of the equation is backwards?
Well, you see, a priori, I didn't know the direction of the friction. I was trying to avoid to give a friction, but if you want to draw a figure, you have to show some direction. And I said that, okay, let the friction force, did we write it over here? Now the friction force, we can say that it is just, if this is the, let's say, x-axis, the friction force is some magnitude in the x-axis. This doesn't really tell me it's in the positive x-axis, this equation. It just tells me that it's along the x-axis. If this is positive, it's in the positive x-axis. If it is negative, it will be in the negative x-axis. I don't really know. But at the end of I was claiming that it was in the negative, in this direction. Some of you were claiming that it should be in the opposite direction. And at the end of our derivations, we had Now, we had seen that the acceleration is slower than what it would have been in the absence of friction. Well, in the absence of friction, there won't be any rolling. If we just put it over there, it will just roll. It will just go slide down without rolling. So it is smaller than g sine theta because of friction. And that tells us that the friction force is trying to prevent its acceleration. So this direction of the friction force was the correct one.
Isn't friction force supposed to act against relative motion of the surface?
True.
In this case, it doesn't.
It does. You see, imagine this. Keep your question. Because, what is happening over here is Here, in this example, we studied the problem describing the rotation as a rotation around this point. So then we saw that there is an angular acceleration pointing into the screen. Here, we calculated the angular acceleration, and from the angular acceleration, we could determine the acceleration of the center of mass. Well, as we said, you can just choose any rotation axis you like, not necessarily this one. For example, you can choose a rotation axis that is the center of mass. If you choose a rotation axis that passes through the center of mass, well, the angular acceleration is still the same, because just like the angular velocity, your angular acceleration is independent of the choice of your reference frame. So the angular acceleration is still into the screen. If angular acceleration is still into the screen, there should be some torque creating that angular acceleration into the screen. Okay, so the friction force has to be in this direction. If there is no friction force, you see, the best way to determine the direction of the friction force is just, if there is no friction force, what would be the direction of the relative motion? So let's assume that there is no friction force. You have this incline. If there is no friction force, the friction force will not be creating any torque, so the object will not be rotating, or will not start rotating around the center of mass. It will just slide down without rotating. So what is the relative direction? The direction, well, the surfaces are just sliding on top of each other. So to prevent this sliding motion, the friction force acting on the ball should be upward. The friction force acting on the inclined plane is downward, by the way. Other questions? Okay, so there's one thing we didn't drive in this example. I just stated it. This one, the moment of inertia of ring for rotations around this point, what I is equal to 2 mr squared. Before, we had calculated the moment of inertia of a wheel for rotations around an axis passing through the center of mass, which was just mr squared. Now it just became 2 mr squared. Now the way we obtain this is basically what's called the parallel axis theorem. Now the problem is, we said that, okay, we can choose whichever axis you like to describe the rotational motion. So if, for example, this ball is rotating like this, I can say that it is rotating around this axis passing through these 2 points. Or I can say that it is rotating around this axis, and this axis is at the same time moving relative to this point, the initial point. I can choose whichever axis you like. The important thing is that the axes that I choose, they have to be all parallel to each other. I cannot change the direction. I am free to choose the axis, but the direction is already fixed. But if I want to study, for example, the kinetic energy of rotation, I have to know the moment of inertia relative to the axis that I have chosen. That means that I need to know all of these moments of inertia relative to any axis which is parallel to one axis. Now, this parallel axis theorem is a theorem that relates those moments of inertia. So let's say that this is my object. This is the center of mass. And we know the moment of inertia for rotations around an axis that passes through the center of mass. But now, for some reason, I would like to describe this as a rotational motion around this point. Let's call that point A. Now, IA is the moment of inertia for an axis passing through A but it has to be parallel. Through the center of mass. Now, in that case, I can just relate the two. We can just show that the moment of inertia around this point A is nothing but the moment of inertia around the center of mass plus m times d squared. D is this distance. This is the distance d. So apply to the previous case. We had already calculated the moment of inertia for an axis passing through the center of mass. It was just mr squared. I am shifting that axis by a distance r. So I have to add mr squared to the moment of inertia to get the moment of inertia around this point, which gives me this 2mr squared. So I don't need to do a moment of inertia calculation all from the beginning. It's enough for me to know the moment of inertia for an axis going through the center of mass. I am shifting that axis by a distance r squared. The only thing we need to do is just prove this one. How do we know that this is true? Well, let's see. This is my object. This is the center of mass. This is the point A. Remember the definition of the center of mass for any axis. I'm just imagining my object to be divided into very small parts, almost point-like. I'm multiplying the masses of that point-like particles by their distances squared from the axis of rotation and summing them up. This is the definition of the moment of inertia. Now let us apply it to the moment of inertia around the point A. Let's say let's just take this point. Or let us take this point. Now let us also choose some coordinate axis to simplify the calculation a bit. This is x, this is y. I can choose another coordinate axis here. X and y. They are parallel to each other. Now this point over here, let's say its distance is r. Its position vector relative to this axis is just r. Its position relative to this axis is r prime. And let us say that this distance over here is the vector d. Now the moment of inertia for rotations around A is nothing but mi, well let's give the index I, times ri prime squared. Just to keep one thing in mind though, these are not three-dimensional vectors. You see, if you take this one, I want to calculate the moment of inertia for rotations around this axis, let's say. Now this point, if my origin is somewhere over here, this point, it has a position vector in this direction. This is the direction of the position vector. Now these are the r vectors over here are nothing but are in fact this vector. So it will give me the distance from the axis, not the distance from the origin. They will tell me the distance from the axis. Is this point clear? Okay, so this is equal to, now our I prime is nothing but d minus, Ri minus d. Squared. I'm just using vector addition. To obtain this vector, what I need to do is reverse this vector d. That is why I have this minus d. It will let me go from this point to this point. Then I add the r, which will allow me to go to my final point. So this vector, Ri minus d is nothing but my Ri prime. Now we will just take these squares, mi Ri squared plus mi d squared minus twice mi Ri times d. Now this is what I want. Ri squared is nothing but the distance from the center of mass. So this is the moment of inertia around the center of mass. This d is just a constant for each one of these small points, so I can just take it out. What remains is the total mass plus md squared. Well, this part is the part that I want to prove, but now we have one additional term. Minus 2 mi/ri dot with d. Here again, 2 is just a constant. I already took it out of the summation sign. D is just a constant. I can also take that out of the summation sign. And then I have this one. Now, does this sum remind you of anything? Position of the center of mass multiplied by the total mass. If I divide this one by the total mass, that would give me the position of the center of mass. What is the position of the center of mass? 0, because I already chosen my origin to be at the center of mass. So the position of the center of mass in this axis is at 0. So this sum is just 0. This is 0. And that kind of completes my proof. That if I know the moment of inertia for an axis that goes through the center of mass, if I shift that axis by d without changing its orientation, then the moment of inertia for rotations around that new axis is nothing but the moment of inertia for rotations around the center of mass plus this mass times this distance squared. Okay, one point that you should pay attention to is that this is not a relation between any two moments of inertia. One of the axes, the moment of inertia, always the center of mass. So, for example, if you know the moment of inertia for rotations, let's say around this point, this axis, if you want to calculate the moments of inertia for rotations around some other arbitrary axis, parallel to the first one, what you should do is first obtain the moment of inertia for an axis going through the center of mass, and then from that center of mass, go to your new moments of inertia, rotation for an axis around this new axis. So the axes over here are not just two arbitrary axes.
I don't understand why does it equal to 0?
Do you agree that this sum should give me the position of the center of mass? Do you remember how we defined the position of the center of mass? The position of the center of mass for a collection of masses, whether it is a solid, rigid body, or two particles, any number of particles, it is defined as 1 over 2 sum over mi Ri squared. No, not squared. Mi Ri. This is the definition of the position of the center of mass. So I say this sum, which is this sum over here, gives me the position of the center of mass. Now, where is the position of the center of mass?
0.
At the origin of my axis.
Yeah.
So this vector is the 0 vector. Other questions? Okay, so let us prove one more theorem about these moments of inertia, and then we can continue. It's called the perpendicular axis theorem. Now, in this theorem, what we will do is, let's just imagine we have a thin object like this keyboard, or you can even take the wheel as an example. And let us suppose that you know the moment of inertia for rotations around such an axis, and moment of inertia for rotations around such an axis. In that case, from these two information, you can just obtain the moment of inertia for rotations around such an axis. This is why it's called the perpendicular axis. We have these two axes, and if we know the moments of inertia through these two axes, we can calculate the moment of inertia around this perpendicular axis. Let's just take our very thin object. This is the x-axis, this is the y-axis, this is the z-axis. Now, if we take any point over here, any mass, the z-coordinate will be equal to 0 for any point. Because it's so thin, and we are assuming that the origin is inside our mass, not exactly 0, but almost 0, approximately 0. That is why we need very thin object. If it is thin, in that case, this approximation will be correct. Now, this point, let's say it will have the position vector, which will be xi in the x direction plus yi in the y direction. Now, the moment of inertia for rotations around the z-axis will be just mi. Well, the distance from the center of this point is just xi squared plus yi squared. This is equal to mi xi squared plus sum over mi yi squared. Now let's look at it from the top. This is our x-axis, this is our y-axis, this is our shape. And we take some point over here. It has coordinates yi and xi. Well, you see, xi is nothing but, oh, sorry, it's wrong. This is xi. This is xi. This is yi. Now, xi is nothing but the distance of that point from the y-axis. So xi squared is the distance squared from the y-axis. If I sum over all the masses, if I imagine dividing my system into very small parts, I multiply the mass with its distance from the y-axis squared and sum all of them up. This is nothing but the definition of the moment of inertia, but the moment of inertia for rotations around the y-axis. It is this one. And similarly, yi is nothing but the distance of this point from the x-axis. So this is mass multiplied by the distance from the x-axis squared, but this is nothing but the moment of inertia for rotations around the x-axis. So this is what we call the perpendicular axis theorem. Now, in this example, this origin need not be the center of mass. It can be any point you want. Just take any point you want. If you know the moments of inertia for rotations around one axis parallel to your thin object, and the moment of inertia of the perpendicular axis that is parallel to your object, if you know these two moments of inertia, then you can calculate the moment of inertia for rotations around the third axis passing through the intersection of these 2 points. Now let's do an application of this for our ring. Okay, we had this wheel. We had calculated the moment of inertia around the center of mass. This was m times r squared. Then we said that using parallel axis theorem, if this is the point A, the moment of inertia around an axis passing through the A which is towards you, let's say, still in this direction. This is m times r squared plus m times d squared. M times r squared, this is twice mr squared. This is what we call the parallel axis theorem. Now, if we want to calculate the moment of inertia for rotations around this axis, let's call it I center of mass prime. Okay, how can we do that? Well, you see, our ring is something very thin, so we can use the parallel axis theorem. So this is one of the moments of inertia that we would like to obtain around an axis that runs on our plane within our thin object. And if we know the other one, let's say this is the moment of inertia, let's call it I center of mass double prime. It is still passing through the center of mass for the time being. For rotations around this axis, it is I center of mass prime. For rotations around this axis, it is R center of mass double prime. What can you say about the two? Will they be equal? Will one of them be larger, the other smaller? Well, you have the break to discuss. Okay, any questions before you go for a break? Okay, see you in 10 minutes.